Well, thanks for organizing a lovely workshop and for the opportunity to speak. So when Eva sent this email asking us to talk about our most recent ideas, I took it quite literally. This is some work that it's very much work in progress. We're in the middle of it. But I thought it would be interesting to speak about it here and possibly hear your thoughts on it. This is work I'm doing together with my PhD students in Cambridge, Theodore Björkman. Okay. The slides don't quite work, but yeah. Well, slow roll inflation is incredibly successful. It gives it solves the classical problems of the hot Big Bang cosmology, the horizon problem, the flatness problem, and it gives a appealing solution to the problem of the perturbations. And it generically predicts adiabatic perturbations that are approximately scale invariant and Gaussian. So it's highly successful. What I will talk about today is not slow roll inflation. It's something different. Part of the motivation for this is just curiosity. It's something different where we want to see what types of inflation models one can actually realize. But it does have some features which could potentially be appealing. One of them is that it can inflate even on steep potentials, while slow roll inflation, traditional slow roll inflation, in particular when the energy scale is low, requires the potential to be very flat. Moreover, small field models of inflation are more sensitive than large field models of inflation to possible problems with initial conditions. So, for instance, if your inflationary field range is very narrow, there could be a problem of overshooting that region of the potential. Moreover, a problem that has already been discussed in New York and the severity is a topic of discussion, I would say, is the problem of the initial patch problem or the problem with initial inhomogeneities. At least the resolutions to those problems are more obvious in high-scale inflation than in low-scale inflation with a small field range. There are some proposals for models.
The point of those results was that no matter how inflation is low energy, you will start.
Yeah. But these are rather sophisticated results and recent results, I would say. Okay. Yeah. And there's a simpler arguments one can make in the case of large field inflation, why initial inhomogeneities. I mean, this is work on by Linde and Flauger and yourself.
That depends on the potential, but the inhomogeneities doesn't matter for the how large inflation. Then, of course, if you start not on top of the potential, you're not going to inflate. Yes.
No, I just meant if there's a small field range, but it's flat but it's short, then I'm imagining that these big inhomogeneities that you can control would include ones that aren't at constant potential energy. They find the exit, or no.
Usually, the inhomogeneous problem was the fact that it's not about staying on top of the potential. This was okay. So, and that does the inhomogeneities usually people. So it was calling a large field and inhomogeneous. So there are two problems normally. Yeah. For small field range, you have to ask why you're on top of the potential. That's not been addressed.
Okay. Just making sure.
Inhomogeneities is that what normally people think about inhomogeneities. I think it's been addressed.
Yeah. So what I'm referring to was if you have a small field range and you have inhomogeneities in a scalar field, you can land down in the vacuum and then you get pulled down and your inflationary epoch shortens. So there are a number of ways in which having non-trivial field space metrics can help problems, at least for model building around these issues. So, for instance, this is some slides or a picture from a paper by Linde a few years ago. Basically, just making the point that if you have a field phi and even if it has a random potential, but it has a non-trivial kinetic term with a pole in it, there's lots of field space in this small narrow region, and if I go to canonically normalized coordinates, the potential subsequently flattens. So the potential is more flat than you would have imagined if you were just looking at it in the regular coordinates. And this is also the motivation behind alpha attractors more generally, where, for instance, the field space can be the hyperbolic plane with a metric like this, and then if you put a random potential there, the same effect plays out. And you can have slow roll inflation in this field space far away from the origin. Now, I want to talk about a different type of inflation that uses the hyperbolic plane. And this is an idea by Adam Brown from, well, a bit more than a year ago. So his proposal was to construct a model of inflation in which, in his word, the inflaton never slow rolls, but it orbits a minimum of the potential and is buoyed by a centrifugal force. And he argues that this angular momentum can naturally start very large, even though it redshifts away. It's enough to sustain a prolonged period of inflation. This idea is a variant of a previous idea called spinflation, in which, well, the authors they considered brain inflation in some warped throat and had some additional angular motion of the brain. In that case, the angular motion of the brain and the additional angular momentum just prolonged inflation by a few e-folds in the onset. While in this hyperinflation scenario, the claim is that this type of angular momentum can make inflation last for a very long time. This is not a highly developed topic, I would say. Apart from Adam's paper, which is 4 pages, mostly words and few equations, nicely written. There's also one paper by a Japanese group from last year. But other than that, there are no substantial follow-ups on this. Okay. So the basic thought of hyperinflation is that, well, consider inflation in the hyperbolic plane. So I gave the metric in the Poincare disk coordinates previously. And the coordinates that Adam used was just canonically normalize the radial direction. And then there's the angular part is here. This field space has a constant negative curvature. And he considered a rotationally symmetric potential. So just some type of potential centered at phi equals 0. Now, this problem has a rotational symmetry in the field space. So there's a conservation of field space angular momentum. And this is, this equation of this conservation equation is also the equation of motion in the theta direction for the background field. But it's useful to define a conserved quantity, the angular momentum. And if one can express the background equation of motion for the radial field phi in terms of this angular momentum, like this. So here, if this angular momentum is 0, we just have we can possibly have single field slow roll inflation in the radial direction. But there is a possibility of trying to balance this term off by this one. So still keeping 3h phi dot small, but having both of these terms not necessarily separately small. Yes, their sum will be small. Now, for that to happen, not just at a point in time or in field space, but throughout inflation, the time dependence of this term and this term needs to be the same. So they need to scale in the same way. So one can write down the required scaling in the large phi limit. So when phi is much greater than L. L, I should say, is the curvature scale of the hyperbolic plane, and I'll consider it to be sub-Planckian throughout. Now, this relation just follows from balancing those terms. Taking a time derivative gives this expression over here. One of the assumptions that is actually necessary to be observationally consistent and to have prolonged inflation is that the second derivative is well, the ratio of the second derivative to the first derivative is given by this expression. Now, 1 over L could be a large number. Here, this is in reduced Planck units. Okay, so clearly looking at this, one can see a solution for the radial direction. The radial direction is no longer driven by gradient flow. The potential doesn't appear in this expression, but the radial direction slowly decreases as it gets rid of angular momentum. The angular speed can then similarly be solved. It's given by this expression. And here one can immediately read off that you need the gradient of the potential to be sufficiently large in order for this to be well defined. So this condition better holds. Now, this is just the equation of motion and neglecting the phi double dot term. It's not actually inflation yet. So one can just plug these expressions into the epsilon h, so minus h dot over h squared. And this is the expression that one finds. Using the equations of motion, one can see that in order for inflation to happen, well, you better have the gradient of the potential over the potential to be much less than 1 over L. Since L can be a small number in natural units, this potential can be quite steep. Now, the field excursion in the radial direction during inflation is obviously easy solved given this, and it's just given by this expression. So to get 60 e-folds of inflation, this field better traveled over many units of this curvature scale. If this curvature scale is sufficiently sub-Planckian, then this total field excursion in the radial direction can still be sub-Planckian. So the summary of these requirements, the potential need to be sufficiently steep, but it's bounded from both sides, and there's also a limit on the potential. The perturbations during hyperinflation get exponentially enhanced just prior to horizon crossing. This comes about by the mass of the entropic perturbations going tachyonic and feeding the adiabatic perturbations. And this enhances the power in the curvature perturbation. So you have your ordinary expression that you perhaps would expect from slow roll, and then an enhancement factor. This enhancement factor, the exponent of it, depends on your speed in canonically normalized speed in the angular direction to your speed in the radial direction. And this enhancement can be many orders of magnitude. This also introduces a sensitivity of the spectral index and of the predictions to the precise value of this enhancement. Clearly, a small variation in the exponent can lead to a drastic variation in the power, and therefore it is the spectral index is sensitive to age. So
Can I ask a question?
Yes.
Just to see if I understand. Is it a multi-field model with a non-trivial kinetic term for the?
Precisely. Yeah. So this is the metric on the field space, and both fields move, right?
Right. And then V of V is just depends on your radial.
Precisely. So you have a rotationally symmetric potential, and this gives you the kinetic terms, and these are the solutions for the background motion.
Okay. And then how do you get how is zeta is related to phi? Is it or delta phi? Is it the usual relation given that it's a multi-field?
Yeah. So that's what I'm skipping over, because it is the motion in along the trajectory. So it's a linear combination of the two that corresponds to the adiabatic mode. So it's not just the perturbation in phi or the perturbation in theta. It's a combination of them. But yeah, I'll show some equations, but I won't actually go through this in detail. Right. So h bar in the models often constructed. So for instance, the models that this Japanese group considered range from 2 to 10. There is an enhancement here with h bar, and eta better be small in order for the spectral index to be compatible with observations. Now, a few remarks that sort of motivated the direction we've gone into is that while the sort of Adam's abstract said that this field orbited the minimum, the change in the angular direction is really exponentially small. So the speed in the angular direction and the speed, the canonically normalized speed in the angular direction are just given by this expression, which is so they're typically of the same order of magnitude. For phi much greater than L, that means that the variation in theta is much smaller than the variation in phi. So what's explored during inflation is a very small region in the angular field space. The potential need not be rotationally symmetric. I mean, a change in the potential along the gradient is not really felt unless, well, if the gradient in the angular direction satisfies this condition. So, for instance, if I take a random potential in R2, so that so that v theta goes like v phi over phi, say, then that would be consistent with this. Okay, so this motivates trying to think about how one can generalize this and phrase it by just expressing it in terms of local quantities around the fields, around the region where inflation happens, rather than what happens in the global field space that actually isn't probed. For the metric itself, this is just a hyperbolic plane. There's nothing special about phi equals 0. That's just a coordinate choice. So the questions that we started to address is try to find a better description. Adam had some words about whether it was an attractor or not, but the computation hadn't been done. Then there is a question of, do you need a large angular momentum initially in order to sustain this? Is that a highly fine-tuned initial condition? And does this type of model extend to multiple fields or more general geometries, or are they highly specific for the hyperbolic plane in particular? These are the questions that I will briefly address in this talk. Then there are additional questions that are important about quantum stability, whether or not these are realizable in supergravity and string theory, and what their prediction for observables are beyond the two-point function. Okay, so in order to generalize this, it's convenient to first phrase it in a way that isn't so reliant on the metric or the particular form of the metric. So a condition from which one can derive many of the properties of hyperinflation looks like this. So it says that the kinetic energy is just given by, or the squared speed is just given by this expression. In the original model by Adam, this expression just comes out like this, just from the equations of motion and their solutions that I showed you. Now, we would also like to phrase this locally, and a good way to phrase it locally is just to express it in terms of the unit vector along the gradient and the perpendicular direction. We take such an orthonormal basis that varies along a field space. And then in order to realize inflation, hyperinflation, one needs conditions on the derivatives, the covariant derivatives of the potential. And these conditions look like this. They look very specific. So it's just like the mixed derivative of along the gradient direction and perpendicular to it vanishes, and this relation holds for the derivatives in the perpendicular direction and the gradient the gradient of the potential. Now these look rather arbitrary, but if one take say a random potential in R2 with this type of relations and go to place it in the hyperbolic plane with the coordinates that I showed you before, and go to large phi, precisely these relations appear. So the gradient direction becomes along the radial direction, and these mixed terms vanishes, and this relation also holds. So this is something that when we do it locally and try to get analytic solutions, we impose, but we'll see that it's a reasonable thing to do. Okay, so in these expressions, one can still write down the background equations of motion and solve them. The solutions look just very similar as in the previous case, which isn't surprising. Now, I would like to show that this is actually quite useful by showing an example of a generalized model of hyperinflation. This model doesn't have any rotational symmetry. First of all, I'll take the metric to look like this. This is a metric on negatively curved two-dimensional space with constant curvature. So it's just a hyperbolic plane. It's not rotationally symmetric. It has some interesting properties that if I take either phi 1 or phi 2 to 0, it reduces to the unit matrix. The off-diagonal terms vanishes. And it's non-trivial in between. I can also consider a very non-rotationally symmetric potential that just depends on one of the fields. So it's just a ramp instead of some rotationally symmetric potential. And then for initial conditions, with this potential, I can just realize slow roll inflation if I go further along in field space. This is just an example of some initial condition. I'll take the value of phi 2 to be 0 and just give a very small velocity in the phi 2 direction. Now, what happens when I do this is that, okay, you start with slow roll. If you start further far enough away in field space, this is completely unsurprising. This is just m squared phi squared inflation. But then after a while, the negative field space curvature kicks in, and you quickly destabilize, and you end up on the hyperfield attractor. This is called geometric destabilization. It's Sébastien Renaud-Patel and Turczynski wrote about it a few years ago. What happens, even if you have a trivial field space metric, you can have a curvature on your field space, a bisectional curvature. And if this is negative, it gives a contribution to the mass of the direction perpendicular to the inflaton. And that contribution is negative, and it can come to dominate over the mass, and then this destabilization happen. So just that I gave a very small velocity to the field space here made this happen. Even if inflation would have gone on for a very long time, even quantum fluctuations could have destabilized it here. Once the destabilization happens, hyperinflation kicks in almost immediately. So here's a period of slow roll inflation, the yellow line. What is it, pink? The pink lines are the theoretical predictions from before, just computed from the potential. So the analytical expressions. So the initial period is slow roll, and then it just settled down into hyperinflation. These are conjugate momenta, the sum of them and the individual components of them, and the predictions are good up to a few percent. So this is an example of sidetracked inflation, or that's what Sébastien Renaud-Patel called it in his paper. What they did was they said that after geometric destabilization, you have sidetracked inflation, but then they in a separate paper consider a different type of model that you can also end up with after geometric destabilization. So sidetracked inflation seemed to be a range of models rather than a specific model. Okay, we also looked at the actual stability of these solutions. So just doing linear perturbation theory around the hyperinflation solutions. And one can show that the Lyapunov exponents are negative apart from a slowly growing mode, which corresponds to an adiabatic perturbation, a perturbation along the trajectory, a perturbation that satisfied this covariant condition that I mentioned. This is the perturbation that will give rise to zeta, and which will be conserved on super Raison scales. One can also generalize this to more general field spaces. We've looked at just the n-dimensional hyperbolic plane, for example. The interesting thing here is that one can do a similar decomposition with the unit vector pointing along the gradient direction, and then one determined by the initial conditions of the velocity. So it's perpendicular to VA. And all the interesting dynamics happens with these two vectors. They evolve and rotate, but the equation of motion can be written like this. All the other fields that are perpendicular to it have trivial equations of motion. So the background solution, again, just trivially generalizes. These additional entropic mode can be light, but they don't get enhanced. They don't have this tachyonic instability close to horizon crossing, which means that the ratio of isocurvature to curvature perturbation gets suppressed by this exponential factor that boosted the curvature perturbation. Okay, so just to summarize, hyperinflation can in principle support inflation despite steep potentials, and it can be observationally consistent, at least at the level of the two-point function. And what I've argued here is that it can be realized without rotational symmetry in a much more general models than was previously considered. It is an attractor, and it can appear following geometric destabilization. So the initial conditions for reaching hyperinflation need not involve tuning a large angular momentum. And it admits multi-field generalizations. This is an immature topic, so there are many open questions, including determining the signals from these models and pinning out the precise relation to other ideas that have been recently discussed, sidetracked inflation among them, and perhaps more importantly, thinking about UV completion and the stability of these models. Okay, thanks.